This is a lecture for Monday, April 20th. We will be continuing our discussion of medical isotopes. These notes were originally written by Daryl Fisher from the Office of National Isotopes Programs. So you can produce medical isotopes using several different techniques. One is using nuclear reactors. You can use charged particle accelerators and proton cyclotrons, as well as linear accelerators or alpha particle accelerators or electron beam accelerators. Now, you can also use chemical separation, starting from longer-lived parent isotopes. Okay, for example, this strontium decay chain or this radium decay chain. First, there's an alpha decay chain that you get from here, whereas this one is a beta decay chain. Now, we're going to talk first about a few nuclear reactors. The first one is actually no longer in operation. It was at Chalk River, Ontario in Canada, and it was the National Research Universal. And this used this was a 135 megawatt reactor using low enriched uranium fuel and high enriched targets. So the idea is you have it contained some container with uranium fuel, and then this uranium will fission, and it will then will spray a lot of neutrons. It will irradiate then the target material that you've put in together with the uranium, and this target material then will then produce the that's being showered by neutrons will then produce the radioisotopes that you want. So, for example, this facility was producing molybdenum 99, iodine 131, iodine 125, xenon 133, and iridium 192. It was a major facility in the world, but it's no longer in operation, and that's why there's some concerns about being able to meet the needs of society now for radioisotopes. Now, the HIFER, the high flux isotope reactor in Oak Ridge, Tennessee, at the Oak Ridge National Laboratory, this one's still in operation, and this uses highly enriched uranium fuel elements. It has the power is 85 megawatts, and it's the highest flux of neutrons from a reactor in the world. It's 44 times 10 to the 15 neutrons per square centimeter per second, and it produces selenium-75, californium-252, tungsten-188, rhenium-188, and nickel-63. You can see some pictures here of Oak Ridge. This is the area where the high flux isotope reactor is located, and here's inside the high flux isotope reactor. Some other nuclear reactors. One is, this is also in operation still, is the Advanced Test Reactor near Idaho Falls. It's operated by the Idaho National Laboratory for the Department of Energy. It's also 85 megawatts, a somewhat smaller flux of neutrons, 4 times 10 to the 14 neutrons per square centimeter per second. And this one produces mainly cobalt-60. So remember, we talked about cobalt-60 as being used as the source of gamma rays to produce gamma rays coming from all different directions to try to kill a tumor by focusing the gamma rays all on that tumor and trying to limit the damage to the surrounding tissue. Here's a picture of the facility at Idaho Falls. Another technique one can use is particle accelerators. So Brookhaven, we talked about Brookhaven. So at Brookhaven, there's a main ring, remember, the relativistic Helion collider, so there's a main big ring here, but there's a smaller ring here called the AGS that feeds to the big ring. So it starts off, you sort of pre-accelerate the ions here before it gets sent to the main ring, and that pre-accelerator part is what's called the alternating gradient synchrotron, and that's also used to produce medical isotopes. Now, obviously, they can't be producing medical isotopes when they're running the relativistic heavy ion collider because um, that will be sort of in conflict with the science mission. But when RHIC is down, the relativistic heavy ion collider is not doing those experiments. They can be used for medical isotopes, but obviously there's some conflict here in that you can't use it for medical isotopes all that often, so there's considerable downtimes. But anyways, the AGS, the alternating gradient synchrotron, will produce a 200 mega electron volt proton beam, and that can be used to then produce, you slam the protons onto a given target, you can produce germanium 68, gallium 68, strontium 82, rubidium 82, zinc 65, magnesium 28, iron 52, rubidium 83. Now, some other particle accelerators are the Isotope Production Facility at Los Alamos, New Mexico, and this is a 100 mega electron volt proton beam at the Los Alamos Nuclear Science Facility, and this is a 0.5 mile linear accelerator at TA. TA stands for technical area. Just a very unimaginative way of labeling things. It's called Technical Area 53 at Los Alamos. And so the main isotopes you can produce is some of the same things we just discussed: germanium 68, gallium 68, strontium 82, rubidium 82, aluminum 26, silicon 32. Alright, so then you can also have commercial cyclotrons. And so here you can have, for example, acceleration of protons or deuterons, which are hydrogen-like, basically hydrogen. The energies may be in the range from 13 to 40 MeV, but some go up to 100 MeV. And these can be efficient and reliable, but they can be expensive. And so you can produce isotopes like fluorine 18, strontium 82, copper 64, and so on. And there are a number of manufacturers here listed here. General Electric in the US. Remember we talked yesterday about a local company in Lansing called Niwave that's making these accelerators for medical isotopes. You see here some pictures of various commercial cyclotrons. 17 MeV, and here's 65 MeV. So let's talk a little bit about what's good for, what makes a good medical isotope. So for applications in medicine, nature and man-made physics approaches provide different radionuclides to choose from. And so the choice is obviously going to be important for the success of what you're trying to do. So the objectives can be one of two possibilities. Either you're doing diagnostics, you're trying to make high quality images of activity in the patient, okay, and you don't want to have much radiation coming out, you just want to be able to do imaging. Now then you can also have therapeutics where you do want a high amount of radiation but localized. So you want to deposit energy that will destroy, for example, cancer tissues, but not other parts of the body. So there are some categories here, broad categories. There are radiopharmaceuticals. So you can have positron emitters, beta, gamma emitters, alpha emitters. So maybe you're using for diagnostics, or you're trying to actually, most of these are for diagnostics. Now you may then be or looking to do therapeutics with various medical devices where you have sealed sources, microsphere applications. So these sealed sources are little capsules we'll talk about with the radioisotopes, or you can have very smaller versions of these with microspheres or nanospheres. Okay, so now here is some of the gamma ray emitters, the standard photon emitters that you can have for imaging. And we talked about molybdenum 99, which beta decays into technetium metastable technetium 99 metastable. And so this then decays with a 6-hour half-life, but is a gamma ray emitter with a 6-hour half-life, and then it can be used for imaging, like you see this nice picture. It's showing the breast tumor. You can do the same thing with sodium iodide. So the sodium iodide, the iodine 131 will beta decay, and that will produce a gamma ray after beta decay. So this can be used both for imaging and for treatment. Indium 111, iodine 123, and so on. Now, you can have positron emitters. So here, you can try to look at cancer metabolism as well as imaging, functional imaging, trying to see what's actually going on, how things are being absorbed. So you can use, in this case, this is highlighting fluorine-18, okay? And so you can have, you can target glucose metabolism by making this compound fluorine-18 fluorodeoxyglucose, and you can then also make a compound with fluorine-18 amino acids to look at imaging various lesions, metastatic lesions. You can also take a look at DNA synthesis by making this fluorothymidine. You can look at what are called FMISO, fluoromazonidazole images to look at what's called tumor hypoxia. That's the starvation, the oxygen deprivation caused by a tumor. And you can also take a look at detection of breast tissue for tumors. Now we can also have therapy agents here. We were talking again about iodine 131. All right, so the iodine will beta decay, and that beta decay will then hopefully the iodine is absorbed by the thyroid, and that can be used to try to knock out the cancer's cells in the thyroid. Now it's also, because after it beta decays, it also emits a gamma ray, and so you can actually image with this as well. Okay, so iodine is very nice because it specifically targets the thyroid as well as salivary glands and the cancers in them. All right, and we can also have therapy agents for various other cases. So these are what are called bone marrow diseases, myeloproliferative diseases. So we have phosphorus 32. Okay, so that's absorbed by the bone surfaces. Okay, and various other applications for bone marrow and such. Now you can have what are called malignant ascites. This is in the abdominal cavity, the intraperitoneal cavity, and you can have phosphorus 32 in some colloid form, or you can have yttrium-90 in silicate, yttrium-90 silicate in some colloid suspension, and you can also have something that's targeting ovarian cancers. And more now about the so-called sealed source medical devices, these little capsules. Okay, so this is this internal radiation therapy or brachytherapy. So you can have for uterine or cervical brachytherapy, iridium 192, cesium 137 sealed sources. You can have implants for iodine 125, palladium 103, cesium 131, and gold 192. And you can have yttrium 90 microspheres for things for the eyes, implanting into the eye for macular degeneration. And here's some pictures of what you can do with yttrium 90 microspheres. So you have a little a capsule you have a thin outer coating here, and then you have a reabsorbable polymer matrix containing insoluble radioactive microspheres. That's all this stuff here. And then you also have some gold bead markers to be able to locate these things easily. Now, then you have some normal tissue, some tumor mass, and you surgically implant them into the tumor tissue. All right. The assumption is that it's difficult to simply cut this tumor out because the surrounding tissue is just kind of in the way, so you just inject these small objects. And then you use some ultrasound to try to remove these thin outer coatings, and then you leave it there for a few days. So yttrium-90 has a half-life of about 64 hours, and so you have some radiation in that tumor region that kills the tumor cells, and then hopefully the patient recovers afterwards. Now you can do something a little bit more high-tech now using viruses. So we're talking all about the pandemic with viruses, but you can actually use viruses for some good. Here, what you do is so this is the virus. Okay, you have the outer part, you have some peptides here, various amino acids, and typically in the interior region here, you have the DNA of the virus. That's what actually it injects into a given cell, and that's how it replicates, by injecting its own DNA into the cell and tricking the cell to replicate the virus. But what you do is you insert a radioisotope, which is kind of a cool idea, in there instead of the DNA, and so now you can use the virus to inject it into the target cell. Hopefully you can get some specificity to get these what are called phages to target a given type of cell, hopefully a cancer cell. So let's finish up with just talking about some of the radioisotopes that are being used. So we talked about gamma emitters, or things that are first doing beta decay, then becoming gamma emitters. So we talked about molybdenum-99, beta decaying to technetium-99 metastable, that becomes a gamma ray emitter. Then iodine-131 is a beta, then gamma emitter, indium-111, thallium-201 also. Then you have these positron emitters. You have fluorine-18, carbon-11, oxygen-15, nitrogen-13, rubidium-82, and so on. You see a really long list here. Now, you also have what are called Auger electron emitters. So that's when you have electron capture. One of the inner levels of one of the inner electrons gets captured by the nucleus. Okay, and then what happens is then you can have, because then one of the electrons one of the outer electrons will fall in to replace the missing inner electron. Well, then what happens then is, often to balance out the energy, another electron, even more outer electron, will get kicked out, and that's this Auger effect, where you have the electron being kicked out of the atom, and that can be a source of radiation that can be used to do treatment, therapy. And you can also have more simple beta emitters, iodine-131 we talked about, strontium-89, samarium-153, holmium-166, yttrium-90 we talked about, and so on. Okay. Now we can also have alpha emitters. So there's obviously a lot of difference between beta emitters, alpha emitters, gamma emitters. The alphas don't travel very far. Betas travel further. Gamma rays go even further. So the alpha emitters are astatine-211, radium-223, actinium-225, terbium-149, and radium-224. And again, these Auger electron emitters, some more here. We have the bromine-77, and we have indium-111, and so on. So a lot of these that we just mentioned will be things that can be produced at effort, which is quite exciting. So that's the end of the discussion of medical isotopes. Thank you for listening.